Hello, YouTube. Today we're going to be talking about necessary and sufficient conditions, use of the word cause, and Mill's causal method. So we talk about causes all the time. You know, we might say that clouds cause rain, or we might say, can't think of an example now. You know, rocket fuel caused or hatred caused him to murder his wife or something like that. And we might mean a whole kind of panoply of things under the word cause. So we're going to break down a little bit, you know, what does that word mean and how do we think about that cause and effect relationship logically? And then we're going to talk about some methods that were developed by the philosopher John Stuart Mill in order to sort of establish relationships of cause and effect. And now these aren't without criticism, but it's kind of like a precursor to what you might think of as the scientific method today, so it's interesting nonetheless. So if I go to my next slide. So what is a cause? Well, a cause is something which gives rise to its effect. So in the examples that I gave, where we might say that a cloud causes rain. Well, maybe if we understand the water cycle to some effect, we know that clouds actually are just evaporated water, and when they reach a certain density and a certain temperature, then they precipitate. The precipitation falls to the ground, and that just is what rain is. Now there's a kind of like logical decomposition of the relationship between clouds and rain. And it's that if there is rain, then there must be clouds. So we might think about, if we see clouds, it doesn't mean that there is definitely going to be rain. I can look out the window right now and see clouds, and it's not raining. But what the inference is that if there is rain, then the rain must come from clouds. What this kind of relationship is what's called like a necessary relationship. So we'd say that clouds as the cause of rain are necessary for the rain. And if we look here, we can see that it's if rain, then clouds as the logical decomposition. Now, in this other example that I've got here, B, rain causes the floor to be wet. So what the logical inference is here is if it is raining, then the floor will be wet. So if we have rain, then the floor is wet. And this is the other way around. So here we were saying clouds are necessary for rain, and so this part of an if-then statement logically, this is the antecedent and this is the consequent, and here we're saying that the consequent is the cause, whereas in this one we're saying that the antecedent, rain, is the cause. And in this case, rain is sufficient for the floor to be wet. What that means is the presence of rain is enough to bring about the floor being wet. Now, obviously, you can probably think of scenarios where those statements aren't quite right, but for the sake of sort of bringing out the logical concept here, I think they do quite well. So we're not necessarily talking. We're not talking about like a chronological cause and effect, which would be, obviously, the cloud happens chronologically or in time prior to the rain. But what we're talking about is the logical relationship. So the logical relationship is that if there's rain, then there must be clouds, which doesn't really tell us anything about the chronology. So let's talk about some of the differences between necessary and sufficient conditions. So a necessary condition must be present in order for its effect to take place. So the presence of the condition does not guarantee the effect. So like I was saying, that's what I was saying before. The presence of clouds as a condition doesn't guarantee that there's rain, but the presence of rain does guarantee that there's clouds, but you could have clouds completely independently. However, removing the phenomena, removing clouds, does mean that there's no longer rain. This is the logical relationship holds, because if we run this backwards, something called modus tollendo tollens, where we negate the consequent, then the antecedent must be negated as well. So it just runs this way backwards, and we can talk about this a bit more later. And in order for an event to take place, so let's say that event is rain, it requires all the necessary conditions to be met. So the necessary conditions might be, one of them might be that there's clouds, another one might be that there's a certain temperature in the sky, another one might be that there's a certain density. I don't know a whole lot about how clouds work, to be honest, to be able to list those off. And we'd say that the necessary conditions jointly are sufficient to produce the effect. Well, what's a sufficient cause or a sufficient condition? Well, a sufficient condition isn't required for the effect to take place. Is that quite right? Oh yeah, so you could have different sufficient conditions, perhaps. So if it's raining, right? Rain is a sufficient condition for the floor being wet. I wrote these slides a while ago, so I'm kind of thinking, like, what did I write here? Did I write something wrong? No, I figured it out. If it's raining, then the floor must be wet. So the rain is sufficient for the floor being wet. But the floor can also be wet because you've spilled a bucket. You are mopping the floor or something like that. Or you've just dropped your cup of tea and that makes the floor wet. So there's different sufficient conditions, but the presence of rain, we're saying in this situation, guarantees the consequent. So the antecedent's presence here guarantees the consequent, and so the antecedent is sufficient for the effect. And this is a modus ponendo ponens, I think, is the Latin. I don't really speak Latin when you expand it out. And even an event, typo there, requires one sufficient condition to bring it about. So there might be, like in that example of the floor being wet, multiple sufficient conditions, but only one of them has to be present. Only one sufficient condition to bring about that effect or event, as I've said. So let's look at the truth tables for some of these relationships. So I was saying in the example before, this is P here and in necessary condition is if there are clouds, and Q here is if it's raining in this table. It's not the same over here. We'll talk about that in a second. Don't worry about that. So as we can see, here's the logical relationship. So if Q is true, then P is true, because we've got Q then P, right? If Q is false, P can be true. P can be true for just some other reasons. There could just be clouds. But what we can't have is Q being true and P being false, because Q guarantees the presence of P, and we could have both of these being false. So this is the relation of a necessary connection. So P is necessary for Q, and this is the logical relationship that we describe. So Q's occurrence requires P's occurrence. P is not a necessary condition for Q. If P is absent when Q is present, so that would mean so if someone said clouds are a necessary condition for it to be raining, and then you could say, well, here's an example of some rain, but there are no clouds, so P would be absent with the presence of Q, the rain. And so in that case, we couldn't say that the relationship is a necessary one. There's no necessary condition there. Whereas in sufficient conditions, it's this other way around, where the rain here being P and the wet floor being Q guarantee, so that if P, then Q. If it's raining, then the floor is wet. And again, we can see in the truth table that both can be true. However, we can see that we can't have it raining and the floor not being wet. So that's not available to us. That's false. Whereas we could have that the floor is wet for some other reason, and it's not raining. And we could have that it's not raining and the floor's not wet. Those are all the logically possible kind of states of affairs if there's a sufficient relationship. So P is sufficient for Q, just in case P's occurrence requires Q's occurrence. P is not a sufficient condition for Q if P is present when Q is absent. So say if it was raining and the floor wasn't wet, then that would mean that we didn't have this kind of relationship. So as I was saying before, the conjunction of all those necessary conditions is sufficient I'm not saying that this is the proper conceptual analysis of knowledge, but anyone who's familiar with philosophy will know that there's a classic account of knowledge, which is as a justified true belief. So to say that someone has knowledge is to say that they have a belief about a certain proposition, that proposition is true of the world, and that they're justified in some way in how they came to form that belief or something like that. And so we can say if someone had a case of knowledge, then we're saying that it must be justified. That's a necessary condition. If someone has knowledge, then it must be true. If someone has knowledge, then it must be a belief. But the necessary and jointly sufficient conditions for knowledge, we would say if we could see something and we were like, oh, it's justified and it's true and it's a belief, then it must be knowledge, because justified and true and belief would be sufficient for something to be knowledge. So that's how necessary and sufficient kind of work logically with each other as well. Now, another thing, a kind of fallacy that we want to be aware of is a false cause fallacy, which is when we wrongly assume that one thing causes something else because we've noticed a relationship between them. And this is something that can happen when we're trying to logically decompose propositions and statements in this way, or relations in the world. So the existence of a mere correlation between two phenomena is never sufficient to identify a causal connection. So just because, we've identified that things of type B always follow things of type A, I think there's a chart online somewhere of films that Nicolas Cage appears in and the number of people drowning in pools in America or something. The existence of the correlation between the phenomena doesn't mean that there's actually any causal connection. The Nicolas Cage appearing in films there isn't actually causing people to drown in pools. If one thing happens after another, we may assume that the first causes the second. Coinciding with something is not the same as causing it, however. This is from the Encyclopedia Britannica. The fallacy of false cause, non causa pro causa, I'm never going to say that to another human being in a conversation, mislocates the cause of one phenomena in another that is only seemingly related when they're not. The most common version of this fallacy is called post hoc ergo propter hoc, after which, hence caused by, which mistakes the temporal sequence for causal connection, as when a misfortune is attributed to a malign event like the dropping of a mirror. And I'm guessing if you kind of follow my stuff and you listen to these sorts of conversations where I talk to religious folks about prophecies and things like that, where they sort of will attribute after the fact these things to prophecy, whereas all the times that it didn't happen, those don't kind of falsify the prophecy that's been made in the first place. So they attribute the cause of a particular event to a prophecy rather than something else. So in order for us to establish that there's a causal connection and not increase the likelihood that we're not just kind of randomly attributing a correlation to we're not just randomly reducing this arbitrary correlation to some kind of logical causal connection. We must understand in some way at least how this causal connection is involved. So like the Nicolas Cage films and people drowning in pools, those just seem completely disconnected. But maybe if someone actually started looking into this, right, and they found out that well, in all these films, Nicolas Cage is really charismatic. It actually turns out that a lot of people copy what Nicolas Cage does. And there's he appears in films and he has this trademark move where he jumps into pools or something. Then maybe we could begin to paint a causal picture. I don't think that this is the case, but maybe we could begin to paint a causal picture. And we can say the same about the clouds and the rain, for example. So when we begin to understand the water cycle, the way the atmosphere works, the way that water works, different kind of states of matter that it can be in and stuff like that, then the idea of this logical causal connection between clouds and rain, it at least makes sense. They're not completely unrelated. So that's a good kind of litmus test for if you're trying to figure out if there's this kind of logical relationship or if it's just some sort of random correlation that you've come across. Okay, so now that we've talked about the language of cause and a little bit of the logic that we want to sort of understand to get our heads around this stuff, we're going to talk about John Stuart Mill to talk about his causal method. But a little bit about John Stuart Mill first. So John Stuart Mill, who was one of the most important English-speaking philosophers of the 19th century, was born in London to the philosopher and historian James Mill and his wife Harriet Barrow. From a very early age, the father took charge of his son's education, imposing on him an unusually strict course of studies. So the young John Stuart Mill began studying Greek at the age of 3. He began Latin, geometry, and algebra at 8, and by 14 he had read most of the Latin and Greek classics. Also by that time he had developed a thorough knowledge of history, scholastic and Aristotelian logic, and higher-level mathematics. At 17, he accepted a position with the East India Company, a private corporation that virtually ruled all of India. He remained there for 25 years, eventually becoming chief examiner, which put him largely in charge of the company. When he was 20, Mill suffered an acute attack of depression that lasted for several months. Although he managed to continue his work, everything seemed worthless to him at that time. This condition was most likely brought on by the severity of his educational upbringing, which had attended to his intellect but left his emotional life a desert. Gradually he pulled himself out by reading the poetry of William Wordsworth. 4 years later, Mill met Harriet Taylor, with whom he became emotionally but not sexually intimate. She was married at that time. Taylor would exert a profound influence on him for the rest of his life. After the death of her husband, 19 years after she and Mill first met, they were married. Today, John Stuart Mill is widely known for his essay on liberty and his book Utilitarianism. The essay is a sustained argument in favour of freedom of speech and the maximisation of individual liberty against the strictures of government. Utilitarianism further develops the ethical theory promoted by James Mill and Jeremy Bentham. As perfected by John Stuart Mill, this theory holds that we should always perform the action that produces the greatest happiness for the greatest number of people. This work was important, among other reasons, for creating an ethical theory that was not based on any theology or religion. Mill also wrote extensively on women's rights, and when he was later elected to a 3-year term in Parliament, he became the first member to urge that women receive the right to vote. Mill's greatest work was his System of Logic, which went through 8 editions during his lifetime. In that book, Mill argues that deductive argumentation, far from being the paradigmatic form of reasoning most philosophers take it to be, is largely bereft of value because it never yields any new knowledge. Also, it is essentially dependent on induction. Thus, it is really induction that should be studied as the primary engine of scientific discovery. In 1858, Harriet Taylor died from a lung infection while the couple were visiting Avignon, France. Nearly inconsolable, Mill bought a house there so he could be near her grave. He died in Avignon 15 years later, and his body was buried alongside hers. So in his Systems of Logic, which I just mentioned there, Mill discusses these 5 methods: the method of agreement, the method of difference, the joint method of agreement and difference, the method of residues, and the method of concomitant variation, and these are used for identifying the causal connections between events. All these examples that I'm going to go over, by the way, are in A Concise Introduction to Logic by Patrick J. Hurley in Chapter 10. So if you're interested in reading more about this and want to do some exercises and stuff based around them as well, they're in Chapter 10, and you can, get the book. I'd recommend getting it secondhand because it's probably very expensive brand new, and do the exercises there. So imagine the following situation. 5 people eat dinner in a restaurant. Jack has salad, French fries, a hamburger, ice cream, and mixed vegetables. Bob has salad, French fries, soup, ice cream, fish, and mixed vegetables. Mary has a hamburger, soup, and ice cream. Tim has fish, mixed vegetables, ice cream, salad, and soup. Gail has mixed vegetables, fish, ice cream, French fries, and salad. Afterwards, all of them became sick from something they ate. Which food caused the sickness? So I've drawn this out for us in this little table. So we have various people, 1 through 5, and then we have different types of food that they've eaten. So 1, 2, 4, and 5 had A, for example, just to help you kind of decode the table if you're struggling. All of them had the phenomena, which in this case is the sickness. But what's a possible kind of candidate cause of the phenomena? Well, we can see that only F is present in all of their meals. So F must be necessary for the phenomenon to be present. So P, a candidate condition, is necessary for Q, is this relationship where the presence of Q, which is our phenomena, guarantees the presence of P. We couldn't say, for example, we can't say that it's E or B, because if this person has the phenomena but they don't have E and they don't have B, so those can't be necessary in that sense. We can't say it's D because this person has the phenomena, and so forth all the way through the table. We can't say it's E or C here. We can't say it's C or D here, and we can't say that it's B or B or D. However, we could say it's F. Now remember what we said about this kind of logical relation, Q then P. So perhaps unfortunate that the phenomena here would be Q, confusingly, and P would be the necessary condition that we're looking for. So if we have not P, then Q, that not P means not Q, not P means not Q. That's the modus tollens where it's running backwards in that logical relationship. So that's how we can say that none of these can be necessary for the phenomena to exist. There's also a few important caveats to mention about this method. So the conclusion that we've got to applies directly only to the 5 dinners represented in the 5 occurrences, and not to everyone who may have eaten in the restaurant. So if some of the food other than those listed in the table, and handily have not actually put the names in the headings, and I don't think anyone's got a good enough memory to remember, but spaghetti wasn't one of them. So say there was spaghetti and that was contaminated, then only if they avoided both spaghetti and ice cream could the other diners be assured of not getting sick. But if among all the foods in the restaurant only the ice cream was contaminated, the conclusion could extend to other patrons as well. This last point illustrates the fact that a conclusion reached by the method of agreement has limited generality. It applies directly only to those occurrences listed, and only indirectly through a second inductive inference to others. Also, because the conclusion yields a cause in the sense of necessary condition, it does not assert that anyone who ate the ice cream would get sick. Many people have a natural immunity to food poisoning. What the conclusion says is that patrons who did not eat the ice cream would not get sick, at least not from the food. Thus, the method of agreement has a certain limited use. Basically, what it says, in reference to this example, is that the ice cream is a highly suspect factor in the sickness of the patrons, and if investigators want to track down the cause of the sickness, this is where they should begin. And then there's a use case for this as well. So an example of an actual use of the method of agreement is provided by the discovery of the beneficial effects of fluoride on teeth. It was noted several decades ago that people in certain communities were favoured with especially healthy teeth. In researching the various factors these communities shared, scientists discovered that all had a high level of natural fluoride in their water supply. The scientists concluded from this evidence that fluoride causes teeth to be healthy. Okay, so now we're going to come on to the method of difference. The method of difference applies only when we're investigating exactly 2 occurrences. And just taking a brief look at this table, you can figure out that basically everything else is the same, everything is identical, but we just have this one difference here. And we have a difference in outcome in the phenomena as well. So this is used to try and identify sufficient conditions. So if you remember the logical relationship, Sufficient conditions, which would be the P in P then Q, if you remember that logical decomposition table from earlier. So P guarantees the presence of the effect. So P is sufficient to bring about Q, we might say. Sufficient condition is present when the phenomena is present and absent when the phenomena is absent. So if you take away the phenomena, then you take away then you've got not Q, so you get not P. And so with the method of difference, we're confined to investigating exactly two occurrences. And a condition cannot be sufficient for a phenomena if it is present and the phenomena is absent. So obviously, F is not sufficient to bring about the... first of all, let's imagine we've got two twins, okay? So we've got two twins who go to the restaurant, and everything is identical about them genetically and so forth, and they've had the same day, they've had all the same meals for some reason, and they've come to the restaurant and sat down, and they've had all the same foods except G here, the ice cream, right? So now suppose someone wants to say, well, I think it was food F that caused the phenomena. Well, we can say, well, food F is a sufficient cause for the sickness. Well, we could say we have here someone eating food F and not getting sick. So whatever we can say has gone on, we can't say that F is sufficient to bring about the phenomena. Same applies for A through E. Whereas when we look at G, we can say that G clearly on its own would be sufficient to bring about the phenomena. And when G's not been present, we've not had the phenomena. So the result brought about by the method of difference applies to only the one occurrence in which the phenomena is present. It's often less susceptible to generalization than the method of agreement, which usually applies to several occurrences. Thus, the mere fact that the ice cream may have caused one of the twins to become sick does not mean that it caused other people in the restaurant who ate ice cream to get sick. Perhaps these other people have a higher resistance to food poisoning than one of the twins, but given that the others are similar to the twins in relevant respects, the result can often be generalized to cover the other people in the restaurant as well. At the very least, if others in the restaurant became sick, the fact that the ice cream is what made Jane sick suggests that this is where investigators should begin to look when they try to explain why the others are sick. But we have to say here that the conclusion yielded by the method of difference is only probable. However, even for the one occurrence to which it directly applies, the problem is that it's impossible for two occurrences to be literally identical in every respect but one. The mere fact that two occurrences occupy different regions of space, that one is closer to the wall than the other, amounts to a difference. Such differences may be insignificant, but therein lies the possibility for error. So rather than reaching general conclusions, perhaps we can only really use the method of difference to try and identify a sufficient condition among those that are present in a specific occurrence. So, maybe this method isn't particularly good for figuring out a specific scientific conclusion or something like that. But maybe actually, if we have two very similar people and one of them got food poisoning and the other didn't after a night out at a restaurant, this is the kind of reasoning we might use to try and figure out what caused one to get sick and the other not to in that way. Okay, so now we come on to the joint method of... I've written argument and difference. I'm going to change that. The joint method of agreement and difference. And now the textbook says about this one that this consists of a systematic effort to identify a single condition that is present in two or more occurrences in which the phenomena in question is present, and that is absent from two or more occurrences in which the phenomena is absent, but never present when the phenomena is absent, nor absent when the phenomena is present. This condition is then taken to be the cause of the phenomena in the sense of a necessary and sufficient condition. To see more clearly how this method works, let's add some detail to the example. So the example is the people in the restaurant. So 6 people eat dinner in a restaurant. Liz has soup, a hamburger, ice cream, French fries, and mixed vegetables. Tom has salad, soup, fish, mixed vegetables, and ice cream. Andy has salad, hamburger, and then the people get sick. The point is that this is represented by the table that we can see. So we can begin by eliminating possible necessary conditions. So we can see where the phenomena is present, and we don't have D. So that means D isn't going to be a necessary condition. Similarly for A, and even though we have two A's here, we can have the phenomena and not have A. So we can see that these three people where we have the phenomena A, B, C, D, and F and G are not going to be necessary. However, it looks like E actually might be necessary, at least in our kind of sample here. But we can also use something like the method of difference, where we can see that when the condition is not present, then we don't get the phenomena. And at least for our sample size, that's been the case every time. So this helps us to say that it's sufficient. So since the joint method yields a cause in the sense of both necessary and sufficient condition, it's usually thought to be stronger than either the method of agreement by itself, which yields a cause in the sense of necessary condition, or the method of difference by itself, which yields a cause in the sense of sufficient condition. However, it's worth noting that when any of these methods is used as a basis for subsequent inductive generalization, the strength of the conclusion is proportional to the number of occurrences that are included. So, an application of the method of agreement that included, say, 100 occurrences might offer stronger results than an application of the joint method that included only about 6 occurrences. By similar reasoning, multiple applications of the method of difference might offer stronger results than a single application of the joint method. And as with the other two that we've looked at so far, we have to remember that any conclusions that we draw are only probable, because some relevant condition may have been overlooked in producing the table. So consider, for example, both salad and soup were contaminated, then the ice cream could not be identified as a necessary condition for the sickness. And if one of at least 3 diners was naturally immune, say, then the ice cream could not have been identified as a sufficient condition. So you can see how those would have kind of corrupted the results that we see, so the conclusions that we'd drawn wouldn't have been correct. Okay, so now we move on to the method of residues, which identifies a connection without regard for the kind of connection, so whether it's necessary or sufficient, or necessary and sufficient. And again, the conclusion only follows probabilistically in this case. So the method of residues consists of separating from a group of causally connected conditions and phenomena those strands of causal connection that are already known, leaving the required causal connection as the residue. So here's our example in this case. After occupying his new house, Mr. Smith found it drafty. He traced the source of the draft to 3 conditions: a broken window in the garage, a crack under the front door, and a broken damper in his fireplace. When the window was replaced, he noticed an improvement, and a further improvement when the weather stripping was installed on the door. He concluded that the draft that remained was caused by the broken damper in the fireplace. So, to sort of bring this diagram here into this example, we have ABC causes ABC. So A, which was the window being slightly open, causes, A, a bit of the draft. And when the window is closed, then a bit of the draft goes away. B, which was a crack or something, causes B, which is another bit of the draft, which then allows us to conclude that whatever C, the broken damper, causes the remain of the draft. That's the conclusion we can kind of get to by having eliminated the other possible causes that are apart. So we've got a few kind of causes that are sort of combining to produce an effect, which is the draft. And by removing all the other possible causes and their effects, we can conclude that whatever cause is left over is sort of the cause of the residual effect on its own. And we could do it by eliminating A and see exactly what B's cause is, however much of the draft, something like that. And again, it's worth noting that the conclusion when we use this method follows only probably, because it's possible that there's a fourth source of the draft that was just overlooked. So now we move on to the method of concomitant variation. Now, concomitant isn't a word that I'd ever come across before basically coming across Mill's causal method. And what concomitant means is just naturally occurring with or occurs alongside. So if you think about the method of residues, where we were sort of removing the known causes of something to sort of leave behind this residual effect of whatever the remaining possibility was. Well, it's sort of similar in the sense that what we're doing is we're varying the causes and seeing what change that has on the effect. So we sort of observe the effect that changing something about the causes has on changing the effects. So we might match, for example, increases in one candidate cause with increases in an effect, or decreases in a candidate cause with decreases in an effect. So here's an example from the textbook. In attempting to diagnose Mrs. Thompson's high blood pressure, a cardiologist noticed a correlation between fluctuations in blood pressure and certain brain waves. As the blood pressure increased, so did the intensity of the brain waves. And as the blood pressure decreased, the intensity of the brain waves decreased. The cardiologist concluded that the two conditions were causally related. So you can see this little diagram down here. So we've got some causes. ABC is coincident with these effects, ABC, and increasing B leads to a reduction in this effect here, lowercase b, and decreasing cause B leads to an increase in B plus. So we've got some kind of like inverse relationship going on, and we'd say that B is causally connected to lowercase b. So just going through the bullet points to recap so far: identifies the causal connection between two conditions by matching variations in one condition with variations in another, increases matched with increases and decreases matched with decreases. So either B causes Y, Y causes B. I don't think we've come to that yet, so let's move on. Why this bullet point isn't making sense, it's because Y here, this lowercase ABC, should have been X, Y, Z, just to make the difference clearer, and I guess I thought ABC would have been better, but now I've sort of changed my mind. So in the blood pressure example that I just read out, we match the increases in one condition with increases in another. For an example that matches increases in one condition with decreases in another, consider this. A sociologist studying divorce noticed a correlation between changes in the national divorce rate and fluctuations in the gross domestic product. As the GDP increases, the divorce rate decreases, and when the GDP sags, the divorce rate goes up. The sociologist concluded that the two phenomena were causally connected. So this second version of the method is like the diagram that we see below, where you've got this negative correlation between B plus the cause, GDP in this case, going up, and divorces going down. But remember what we said before. So the existence of a mere correlation between two phenomena isn't sufficient to identify a causal connection. In addition to the causal connection suggested by a correlation, the supposed causation must at least make sense. So if we consider this example, that after an in-depth study by researchers, they discovered a correlation between the price of pork belly futures on the Chicago Mercantile Exchange and earthquake activity in Japan. As the number and intensity of earthquakes increased, the future prices also increased, and vice versa. The researchers concluded that the two phenomena were causally connected. Now, in this case, this argument is clearly weak, because it's pretty much inconceivable that either of these phenomena could cause a change in the other, or that the changes in both could have a common cause. It's more likely that the correlation is just purely coincidental here. And that's the same with the Adam Sandler movies or whatever I mentioned earlier. So you might be thinking, like, this method is maybe a bit useless and might lead you to sort of establishing some of those false causes that we wanted to avoid, as mentioned in the earlier slide. But this method is useful when it's impossible for a condition to be either wholly present or wholly absent, as was required for the use of the first three of Mill's method, the agreement, disagreement, and agreement and disagreement. Many conditions are of this sort. For example, if you think of the temperature of the ocean, the price of gold, the incidence of crime, the size of a mountain glacier, a person's cholesterol level, and so on. If some kind of correlation can be detected between variations in conditions such as these, the method of concomitant variation asserts that the two are causally connected. The method has been used successfully in the past to help establish the existence of causal connections between smoking and lung cancer, for example, nuclear radiation and leukemia, and alcohol consumption and cirrhosis of the liver. I included everything that I just said on the next slide, but forgot to skip slides. But yeah, so be careful to avoid attributing a false cause if you're thinking of using this method, and suggested causes must at least make sense. The causal explanation that's being offered, but it's still useful when it's impossible to have our conditions be wholly present or wholly absent, for example, and those use cases that I just mentioned. So you might have noticed that Mill's methods closely resemble certain scientific methods that are used to establish causal connections and correlations. So the method of difference is virtually identical to the method of controlled experiment employed in fields like biology, pharmacology, and psychology. A controlled experiment is one that involves two groups of subjects, an experimental group and a control group. The experimental group includes the subjects that receive a certain treatment, and the control group includes the subjects that do not receive the treatment but are otherwise subjected to the same conditions as the experimental group. So the simplest type of controlled experiment involves an experimental group and a control group, each consisting of just one member. So 2 mice, for example. I mean, a lot of the methods were sort of around finding like a correlation in a particular case, and a correlation can at least suggest a causal connection, and then once a correlation has been established, a controlled experiment can be designed to help identify if there is a causal connection or not. So there's this example in the textbook where in the case of TV violence, a group of children could be randomly divided into an experimental group and a control group. The experimental group could then be exposed to violent TV shows for a certain period, and the control group would be exposed to non-violent shows for the same period. Later, the behavior of the children in both groups could be observed, with every act of aggression noted. If the experimental group displayed more acts of aggression than the controlled group, the conclusion might be drawn that TV violence causes aggression. Experimental procedures resembling Mill's method of concomitant variation have also been used in the physical sciences to identify causal connections. For example, in the early part of the 19th century, Hans Christian Ørsted noticed that a wire carrying a current of electricity could deflect a nearby compass needle. As the current was increased, the amount of deflection increased, and as the current was decreased, the amount of deflection decreased. Also, if the current were reversed, the deflection would be reversed. Ørsted concluded that a current of electricity flowing through a wire causes a magnetic field to be produced around the wire. To recap and summarize some of the things that we've talked about, cause can be kind of ambiguous in language. We might talk about one thing causing another thing, but the logical relationships between those causes and their effects can be quite different. So necessary conditions, for example, which have this kind of relationship, are quite different from sufficient conditions. So we might say, that cars driving around the city cause smog, by which we mean that if there's smog, then there's cars driving around the city in this sense. And so removing the cars driving around the city, removing the necessary condition, in which case removing just one of the necessary conditions is enough to stop the smog in the city, and we don't have to then remove all the other necessary conditions as well. So it's useful to think about causes in that way. Whereas a sufficient condition is one that's sufficient to give rise to its effect. So this is the relationship that if the sufficient condition is present, then the effect is guaranteed to be present. And then there's this whole discussion around, can you have like multiple different sufficient conditions giving rise to certain effects? Particularly interesting when we talk about, the philosophy of mind at certain observations that we might have made. Then we talked about Mill's method, the method of agreement, the method of difference, joint method of agreement and difference. And those three were to do with, the complete absence of present, or the complete presence or absence of a phenomena and certain causes. And again, they were kind of probabilistic. The conclusions that we could draw from them were tentative at best. And then the method of residues and concomitant variation, which were more to do with this kind of like continuous changes rather than complete kind of removal of a change, where the method of residues was to do with removing all of the known causes that give rise to an effect and seeing what's kind of left behind, and hypothesizing that, well, whatever causes are left behind, specifically caused that bit of residue. And the method of concomitant variation, which was to do with kind of finding these correlations between increasing a specific variable and seeing what happens to the effects. So causes can be described in terms of sufficient conditions, necessary conditions, and sufficient and necessary conditions. Mill's method, named after John Stuart Mill, are inductive techniques that allow us to identify causal connections. The method of agreement identifies necessary conditions. The method of difference identifies sufficient conditions present in a specific occurrence. And the joint method of agreement and difference identifies sufficient and necessary conditions. The method of residues and the method of concomitant variation identify causal connections without regard to the kind of causality involved. The methods of agreement, difference, and concomitant variation resemble certain methods used in the natural sciences and the social sciences to identify causal connections. Okay, so I'm going to wrap it up there, and I hope you've learnt something. I hope it's been useful. If you have any questions or future videos that you'd like to see done in this format, let me know, and let me know what you think of this format, because it's slightly different to usual. Thanks, and bye.